Welcome to another past paper guy video. I'm going to be solving the paper 3 section A June 2018 AQA paper. Now, this is a hard paper. As always, I suggest looking in the section below and getting the paper and doing it yourself first. So without further ado, let's go. Right, question 1. There's an awful lot to read on this paper. There's an awful lot going on, and there can be quite confusing questions. But essentially what we've got is we've got a pivot here, and we've got a moment being created by the weight of the ruler acting down here, and we've got a force acting upwards here, which is balancing it. And so what we're going to do is we need to use principle of moments to calculate the weight of the ruler. And to do that, we need the distances involved. Well, the pivot's at the 1 centimetre mark, which it says there. So the distance from the pivot to the force, which is at the 30 centimetre mark, is 29 centimetres. And the distance from the pivot to the centre of the ruler, assuming that it's a uniform ruler, is 49 centimetres. Now we're deducing the mass of the ruler. We could convert the weight here, the force here, that's 214.66 grams worth of force. We could convert that into newtons, and then we would get a newton's value for weight, which we could then convert back into grams. But we might as well just leave it as is, because all the conversion factors will cancel at each stage. So we're using the principle of moments. Whenever you use the principle of moments, say so. So we've got sigma clockwise is equal to sigma anti-clockwise. So the clockwise moment is going to be W. So we've got, it's going to be M G, which is W, times by 49 is going to equal this force here. So that is 214.66 G, so the G's immediately cancel, you see, times by that distance there, which is 29, and so M is equal to 214.66 times by 29 divided by 49 there is equal to 127.04. So I'll put that in there, and it was 436. And the assumption that we've made, well, the most obvious one is that the ruler is uniform. Okay. Right, question 1.2. So they've added this wire here, which they're putting a current through, and all of this has added a little bit extra to the force here. And then they're applying a magnetic field here in order to create an extra force on the wire going up or down. So the first thing we need to do is we need to state and explain the direction of the horizontal uniform magnetic field. Okay, so there's a couple of things going on here. The first thing we need to work out is, does the force increase or decrease as the current increases? So from this graph here, as the current increases, the number that's red here is decreasing, which means that as the current is increasing, the force must be going upwards. So that's the first thing to do. So I'll leave the state for the moment, just to explain it for the moment. So as the current rises, the mass reading falls, so the force due to the magnetism, or the magnetic effect, magnetic field, that's it, is up. Right, the next thing we need to know is which direction the current is. So the current's going from positive there to negative there, so it's going left to right. The current is left to right. And then we need to say what we're going to use to do it, and we're going to use Fleming's left-hand rule. So using Fleming's left-hand rule, we get this. So we need the force to be going upwards, the field must be going into the page because the current's going across this way. So the current's going that way, so the field is into the page. Okay, so field is into the page because the current's rising as the mass, as the current rises, the mass reading falls, so the force due to the magnetic field must be pulling upwards, which would reduce this reading here. If it was going that way, it would obviously be squeezing down on this, making this reading bigger. The current is left to right. Fleming's left-hand rule gives you the answer. Okay, so in this one, we've got an equation here, and we're going to be using this graph and the previous page to try and determine what's going on in this equation. So let's use the previous page first. We're going to need to have L. L is the length of the region where the magnetic field cuts through the wire. So that here is 1, 2, 3, 4, 5 millimeters. So L is equal to 5 times 10 to the minus 3 meters. And that's from page 4. Okay, so sigma is the change in force acting on the prism per unit current in the wire. So it's not the force acting on the wire for the magnetic field, it's the force on the prism, which is what we're measuring here. But here we're measuring it in terms of grams, so we're going to need to convert grams into newtons before we can do this. And then because it's the change in force per unit current, it's going to be the gradient of this. So we're just going to be able to divide by the current here. So let's start then. Sigma is equal to delta F divided by delta I. Right, so delta F, we're going to get a negative value out because this is a negative line here. So we'll just use the whole of the line. So we're going to have the final value, which is 237.5. Take away the initial value, which I make as 238.48. I think that's, I never have nice graphs. So that's going to be 42444648. Yep. So that is the change in the mass. Right, now to change that into a force, we're going to need to multiply by G, and we're going to need to change grams into kilograms as well. So times by 10 to the minus 3. And then we need to change, divide by the change in current. Well, the final value of the current there, that's 4.5. That's 4.6, so it's 4.55. Take away 1.0, and there's nothing else to do there. So I just need to do this calculation here, and we get 237.5, take away 238.48 is equal to that, times by this conversion factor, and we need to divide by this, and we get minus 2.70811 times 10 to the minus 3. And then we need to work out what B is. Well, B is equal to sigma divided by 3 L's. So that's minus 2.70811 times 10 to the minus 3 divided by 3 of those. So So 3 times 5 times 10 to the minus 3. So we're going to divide that by 15 times 10 to the minus 3. And we get minus 0.18054. So minus 0.18 Tesla. Question 1.4, there's a lot of text going on here, but what we need to do is we need to figure out what effect on these 4 quantities is going to be by pivoting the ruler from this side to this side. So there's an amusing thing here. You can see that they've actually marked the field going into the page here, which they probably should have removed. But anyway, nothing else has changed from figure 3, which was the earlier one. So everything stays the same apart from you've moved the pivot from here to here. Right, so let's go through them then. The force acting on the current carrying wire due to the horizontal uniform magnetic field. So nothing has changed on that. It doesn't care where the pivot is. It's not going to make any difference. So there's still going to be a force up here, and it's still going to be the same. So there's going to be no effect on that one. The force acting on the prism due to the pivoted ruler. Right. Well, before the pivot was here, and so we were that far from the pivot, and the weight was that far from the pivot. Now, instead of it being 29 centimeters, it's now, what's that, 69 centimeters away, so that the moment of the weight force around this pivot is equal to the moment of the weight force around that pivot. But now, because this one's further away, the force going up needs to be less to create that same moment, because you've got a longer distance there than it was when it was there. You need the same moment, so you need a smaller force. So the force is going to reduce there. The gradient of the graph. Okay, well, so the gradient of the graph is affected by how much this has an impact on the value here. So we're going to have the same range of change in force, so we then need to work out what the moment effect on this point here will be, about this pivot. So if the force has the same changes in the previous one, if I go back and get it, the moment was this distance here times by the force that was acting up there. Now the moment caused by this is going to be this distance here times by that force, which is a much smaller moment. So it's going to have a much smaller effect on this reading, which means that the reading will change less, so it will be shallower, so it will have a reduced gradient. The vertical intercept of the graph, well, this is kind of the same as asking question 2, because the vertical intercept of the graph here is when the current is 0. So it's up here. It's when the current is 0. Well, we already said that when the current was 0, all of the reading on here is going to be due to the weight of the ruler, which we've said is less because this distance is longer than this distance, so that one will also be less. And there's an enormous amount to think about in that question for 3 marks, but there we go. Right, question 1.5. There's a big blurb here, but the question is that what we need to do is we need to add a circuit here to make it so that the current through this and the current through this are identical. and they're going in this direction. Well, current is going to be coming out like that, isn't it? So to make them identical, we need to put them in series, is the idea that it's getting at. If you want the currents to be identical, you need to put them in series. So we want to hook that to there, and hook this wire to the end of that one, and then hook this wire to there, like so. And the current has to go through there, through that wire, through there, through that wire, and back there. So they're in series, and so they'll have the same current. Okay, in this question 1.6, we are going to use this apparatus here to try and show this relationship here. Now, we're told that we want to find K, but we're only allowed to vary one of these things. So the experiment procedure should involve only one independent variable. So you could pick either D or I. I'm going to pick I because it's on the top, which makes it generally easier, and I think it's easier to measure as well because you're just using an ammeter. So we're going to vary I and measure F. Right. So the first thing I want to do is I want this exact setup. So I'm going to set up the experiment as figure 6. I'm then going to measure D using a rule, and we want to keep D constant. For the rest of the experiment. So it doesn't matter what D is as long as it doesn't change, and we'll have a fixed value on the bottom there. So once we've measured D, we know L, we can measure L, so let's write that down. Measure L using a ruler. So now we need to take our actual measurements, and for that we're going to be measuring I and F. So the easiest way to do this is going to be if we can set F to 0 to start with. So if we then, with the power off, if we tear or reset or 0 the balance, okay, that means that it's now going to be reading 0 when there's no current. So then we have our actual procedure, which is turn on the power and record the current through the ammeter, and that is, we're calling I. And the mass on the scale, which we'll call M. So let's just have a quick thing. So we're going to have I in amps, we're going to have M in grams. We need to plot I squared against F though. So we want to calculate I squared in amps squared. So we need to we'll do that in a moment. First of all, we then repeat this step for different values of I from 0 to, what was the maximum? It said maximum is 5 amps, so let's go for 4.5 amps. Okay, so we got like 0, 0.5, so that'll be 0. 4.5. We're going to work out what I squared is, so calculate I squared, and we also want to calculate F, and F, which is, so F is going to be M times by G divided by 1000, to change it into kilograms and then change it into a weight. And then plot F versus I squared, because we've got F there and I squared there. So we've got y is equal to mx plus c, and well, that one corresponds to that one corresponds to that one, and that all of this corresponds to m. So the gradient m will equal KL over D. So therefore K is equal to the gradient times by D divided by L. So plot F versus I squared, and then calculate a gradient. And then K is equal to the gradient times by D, which we measured up here, divided by L. And that's the result there. Right, question 2. So we've got this rather strange experiment where they've got a tape measure and they're bending it. Looks rather exaggerated here, but it's bending, presumably under its own weight, off the end of a table. The first thing we're asked to find is how we would measure y. So the best thing to do with this is to draw something onto the table. Now there are more than one way that you could do this, but this is the way that I thought you could do, which is if you placed a meter rule here, like so, so we have a meter rule, and we need to get that vertical, so I'm going to use a spirit level to get it vertical in case the floor isn't flat. Okay, so that's the level. So the things with the little bubbles in, that's what we're going to put there. And then what we need to do to find y, we need to see that measurement there, which I'll call B, and that measurement there, which I'll call A, and we need the difference between A and B. So, right, it's not quite clear how much it wants for 2 marks, but let's do this all properly. So, fix a vertical meter rule behind the tape as per the diagram. Use a level, or you could use like a plumb line or something, to check it is vertical. You could also use a set square with the floor, but that assumes that the floor is flat, so I wouldn't do that. Then get eye level, so that's to reduce parallax error, and note the values A and B at the top and bottom. Y is equal to, it's going to be the value of A minus the value of B, or the other way around, depending which way you got the rule around. There we go. Question 2.1. By changing the extension of the tape, students obtains these values. Suggest why the students make all measurements greater than 70 centimeters. Well, if we look at 70, then presumably these are just getting smaller and smaller and smaller, but are never quite zero. They're never going to, this tape's always going to be sagging down a tiny bit, but it's just going to be tinier and tinier. So that will mean that you'll have very large percentage uncertainties for smaller measurements. So the value of y for small, or for not small, but values of x that are less than 70 for so the value of y for values of x less than 70 centimeters will be very small, leading to large percentage uncertainties. Okay, so that's all you need for that. It's just one. Okay, 3 marks. What we've got to do now is they've plotted the data for us. They've given us this relationship between these values, which are on the previous page. And we need to find out what n is, and it says that n is an integer. So we need to make sure that our final answer we write down an integer. Right, so let's do some maths on this first. So we start with y is equal to ax to the n. So we know that log y is equal to log a plus n log x. And we equate that to y is equal to mx plus c as a straight line, and we're going to be plotting log y on the y-axis. We're going to be plotting log x on the x-axis. The gradient is going to be n, and the y-intercept is going to be log c. So we first of all need to draw a best fit line on this. So there's quite a lot of places that you could draw this. I think because we're just looking for an integer, then it's not going to be too bad if we're a little bit out. So one above, one below, one below, one above, one below. Let's go for there. See how that does. Okay. So we need to find the gradient if we're going to find what n is. So let's pick a nice value here. There, it goes through a nice value. And that is going to be 2.125 there. And across here, make sure that you include your drawings on the page. Just slipped a bit there. I think that should be a little bit higher. So that's going to be 1.77. Okay, and then here, this value here is going to be 0.725. Right, and then we need to find the gradient. Gradient is equal to, so difference in y is going to be 1.77 final value, take away start value, 0.725 divided by final value of x is 2.125. Take away start value 1.85. So let's try that. So 1.77 take away 0.725, which is about 1, divided by this fraction, or this sum here. Take away 1.85, which gives us 3.8 exactly for that particular thing. So remember, when we're working out what n is, it's an integer, so we write 4, not 3.8 there. Question 2.4, we're trying to explain how we find a numerical value of a. We don't actually have to do it, but we still have to describe what it is. So the first thing we need is the equation of this line. So the first thing we need to do is find the equation of the best fit line. Right, and to do that, we can use the gradient that we already have. So in the form y equals mx plus c is what we want. So we want y is equal to mx plus c. And this is the gradient calculated in part 2.3. Right, we can then substitute in a value, any point along here, of y and x. So then substitute in any value of y and x, well, they're going to be log y and log x, aren't they? So y and x, so that's log y and log x. Okay, to find c. And so then we'll have an equation of the form y equals mx plus c. And so once we've got an equation of y equals mx plus c, we know what c is. And if you remember when we did this, c was equal to log a. So log a is equal to c, the intercept. And then we would have 10 to the power c is equal to a. So we just need to inverse log that, which is 10 to the power c. Estimate the order of magnitude of a. You should use data for x and y from one row in the table on page 11. So we have to flick all the way back to page 11 now. Here it is. And we're going to estimate the order of this. Now we also need a different page. We also need page 12 because we need this equation here. So y is equal to ax to the power n. So I'm going to pick this row here. So x is equal to 116.8. Now be careful because you're going to be flicking backwards and forwards in the paper that you copy things down accurately. It's really easy to make a mistake when you're changing from piece of paper to piece of paper. So these are both in centimetres. So we've got a is equal to y divided by x to the 4, which is equal to 3.7 divided by 116.8 to the power 4. And we only need its order of magnitude. So here goes 3.7 divided by, you could, I suppose, do this in your head, but I'm just going to put it in the calculator anyway. So we've got about 2-ish times 10 to the minus 7. So the power is minus 7. The units of A, well, this is in centimetres here. This is going to be in centimetres to the power 4. So this is going to be centimetres to the power minus 3. So there's one of those will cancel and you'll be left with 3 centimetres on the bottom. I suppose you could do that by converting both of these into metres first, and that would change your order of magnitude as well. By a factor of 6, by 6 orders of magnitude. Question 3. Right, there's quite a lot going on in this experiment. It's quite a lot to take on board. Once again, it's a lot of reading. But let's try and summarise what's going on. We have a flask here and we're placing it in hot water and it is exposed to the atmosphere. So the pressure inside that flask is going to be atmospheric pressure because it's open to the atmosphere. And we're going to let it get into thermal equilibrium with the water. So it's going to have the temperature of the water and it's going to have an amount of gas in there. Once it's stable, we're going to seal this valve, which traps that amount of air in. So if we think about the ideal gas law, we've got PV is equal to nRT. So we've changed the temperature of the gas. The pressure is atmospheric pressure, so we kept the pressure constant, and we have then trapped a certain amount of gas in there. So that's going to allow us to keep N constant throughout the experiment by trapping that amount of air in. We're then going to place the flask into a colder bath of water. So this one is at room temperature. So it's not going to matter whether the flask is inside or outside of the water, it should still be the same temperature. And we're going to let it change its temperature so that it is the same as the bath. Remember, this valve is sealed. So inside here now, the pressure will be reduced because we have reduced the temperature. So the pressure kept volume constant, kept N constant. So the pressure will be less in here than it was at atmospheric pressure. We're then opening the valve and water is going to push its way in, because the water up here is going to be being pushed down by atmospheric pressure, and the air inside here is going to be pushing back, and these two are going to normalize, but there's going to be a difference in the pressure here and here due to this height, because the pressure of this air is going to be bigger than the pressure of the atmosphere because of this extra head of water here. Now, to get rid of that, we raise the flask up so that this is at a constant level now. Now, the pressure here and the pressure here, due to the atmosphere, are the same. So now what we have is the pressure in this vessel here is the same as it was in the very first part of the experiment. And then we seal this off again, trapping that amount of water in. So we've essentially reduced the volume of this flask by allowing some water to fill the space until the pressures are the same. So between here and here, the pressure is constant, the number of molecules is constant, but the volume is smaller and the temperature is smaller. And so we want to see whether volume and temperature are directly proportional to one another. That's the idea. Okay. So explain why the volume of the air in flask figure C is less than the volume of the air in flask figure 9C and 9D. So that's what I was trying to explain about this extra head of water here. So the pressure in flask 9C is higher than in 9D because there is an extra head of water, let's just call it H, which increases the pressure due to the atmosphere. So the pressure inside this flask is caused by atmospheric pressure plus this extra head of water here. Now, that was my answer when I did this first, but I'm not sure that is the answer that they wanted. I think they wanted it in terms of this, which is saying that N, R and T are all constants. So by Boyle's law, then if the pressure is bigger here, the volume will be smaller. So I'll add that in as well, but I don't think that's the first thing that, well, that's definitely not the first thing that came into my head when I asked this. Explain why the volume here is. The reason why is because the pressure is different, but I guess linking that back to your known physics is by Boyle's law, because N, R and T are constant, because remember this is all at room temperature here. P is proportional to 1 over V. Okay, so that will tell you the relationship between the pressure there and the volume. Question 3.2. Explain why Charles's law can be applied to compare the flask in figure 9A and 9D. So once again, we have to flick between pages. We need that diagram there, and we need this diagram here. So the reason Charles's law can apply is because the pressure in this and the pressure in this are both atmospheric pressure. So we need to make sure, for Charles's law, we need to make sure that one's constant, that's obviously constant, and we need to make sure that is constant. So, and then we've got V is equal to, is directly proportional to T. So, in 9A and 9D, the pressure of the air in the flask is atmospheric pressure. And the other thing that is the same is we've trapped the air in 9A, so it's the same amount of air that's in 9A as in 9D. And the same mass of air in 9A here is in 9D, as no air is allowed in or out. Okay, so we sealed off this valve, and then that means that the amount of air inside there and there is fixed. The flask is removed from the bath C, and the valve and stopper are removed. We've got some water here, that's volume 1. We also then have the flask and we completely fill it with water. The volumes V1 and V2 are shown. Explain how V1 and V2 can be determined. In your answer, you should identify a suitable measuring instrument, explain a suitable procedure to eliminate possible systematic errors. Okay, well, the first part's reasonably easy. Figuring out what they mean by this is just anybody's guess. So let's do this then. So the easiest way to do this would be to use a measuring cylinder. So we just pour this liquid into the measuring cylinder. So pour the liquid V1 into a measuring cylinder and repeat with V2. Okay, so they don't want any more than that. And then what they're actually after here is how to use a measuring cylinder. And the method that you could use is to make sure the cylinder is on a flat surface. Get eye level and read to the bottom of the meniscus. Now that's where I left it when I did this the first time, but they wanted you to actually name the error. They didn't say that they wanted you to name the error, but they want you to name the error. So what they actually want here is to avoid parallax errors. Okay, to avoid parallax errors. Not quite sure if it's got a double L or not. And that is how you do 3.3. So just pour it into a measuring cylinder. There's an alternative way. You could measure the mass of an empty one on an electric balance, then measure the mass and making sure that you've got the plug and everything on as well. Then measure the mass of one with this much liquid, and then measure the mass with one with this much liquid. And then from those, you can use the fact that rho is equal to m over v. So v is equal to m over rho. And you use the density of water to calculate the volume. So that's an alternative method. 3.4. This question's straightforward when you know what on earth it is that you're supposed to do. We need to plot the points here. These readings, which were on the previous page, for V1 and V2, are not what you're going to plot on this. What you need to plot is you need to plot the temperature readings and the corresponding volumes of air inside the flask. So when you have the high temperature here, we have the whole of the flask is filled with air. So that, it's so much flicking backwards and forwards, is volume 2, isn't it? So that's volume 2, which is equal to 255 centimeters cubed. Now when it's cold, you don't want that one. You want this one here. Now that liquid there is volume 1. because that's it there, turned up the other way. So this volume here, volume 3, is equal to volume 2 take away volume 1. So that one is volume 2 take away volume 1, which is 207 centimeters cubed. So those are the values that we need to plot. We've only got 2 points to plot. So we need to plot this point here and this point here. So we've got this one scale already marked, so we need to go from 207 to 255. So if we put 200 here, 210, 220, 230, 240, 250, 260, then we're going to be plotting that much, which is more than 8 centimeters and more than half of the scale. So that's going to be enough to plot. So we need this point here, which is at 19. So 19 is halfway between that box and that box. And we need 207, which is there. So we're going to have that point there. And then we need at 86, well that's 90, 86 is there. And we need 255, which is nice and easy. 255 there. And then we will add a best fit line to figure 11. I mean, we have 2 points on our best fit line. So a best fit line with 2 points needs to be a line that goes straight through those 2 points. There is no other line that you can draw. The final question, 3.6, determine the value of absolute zero using the graph here. So what we need to do is we need to extrapolate this line here made from these 2 points all the way back down until the volume is equal to 0. And when the volume is equal to 0, we know that all molecular motion is stopped, and that's the temperature of absolute 0. So the first thing we really need to do is to work out what the gradient of this graph is. So let's do that first. So the gradient of the best fit line is going to be, right, let's find some values. So that looks like 265, and then here, let's see if we've got a nice point that's going through there. So at 30 it is 215, and we've got 1, 2, 3, 4, 5, 6. Oh, that's not enough. We need it to be 8 centimeters minimum, so we're definitely not going to do that. So let's just use the whole graph. So this temperature there is 24689 degrees centigrade, and that volume there is 200. So the gradient of the best fit line, which is going to be in centimeters cubed per degree centigrade, is going to be 265 take away 200 divided by 100 take away 9. So that's just 65 divided by 91. So 65 divided by 91 is equal to 0.714285 ... and the units of that, although we're not going to need them, are centimeters cubed per degree Celsius. So let's think about what this graph actually looks like in the grander scheme of things. So we've got at 9 degrees there, and we've got 100 degrees there, and it's sort of going between 200 and 265 there. And it looks like that, and it's going to hit when V is equal to 0, and this is going to be minus 270-ish degrees. But the axis that we've got here with our origin is here. So this point here is our y-intercept, which is just here. If I'd been sensible about this, I could have drawn this whole graph up a little bit, and I actually would have been able to, for once, fit the y-intercept on the graph. But I haven't. So we need to work out what this is, and then we need to extrapolate all the way back to when v is equal to 0, and we'll get theta, the corresponding value of theta. So we know the gradient, so now we need to find the y-intercept. So we've got v is equal to the gradient times by theta plus c. So let's pick a point. Let's go for this point here. So 200 is equal to the gradient 0.714285 times by theta, which is 9, plus c. So c is equal to 200 minus 9 times by 0.714285. Right, so let's, so we times that by 9, we do 200, take away our answer, and that gives us c is equal to 193.57. Okay, so we've now got the equation of the line. So we've got v is equal to 0.714285 times by theta plus 193.57. Now that makes sense that this is intercepting here at about 193, so that seems appropriate. Now we need to let v equal 0 and find out what theta equals. So theta is going to equal minus 193.57 divided by the gradient 0.714285. So we need to divide that by 0.714285, and remember that's a negative number, and we get theta is equal to minus 271. Okay, that's the 3SF. Probably 2SF is more appropriate, so that's 270 2SF, which is probably more appropriate. Right, and that is that paper. It's possibly not as hard as previous years, but there's still a lot going on, and the questions are not straightforward. They're quite convoluted. So hopefully you found this video helpful. If you have, please do press the like button and subscribe. Make comments, it helps me out, and share it with your friends. Thank you.